Um, so anyway, this is the second part of an embedded operating system class that I taught for 4 years at the UW. Basically, I taught the second session of three, and the session I focused on was the actual operating system itself and how. And so basically, over the years, I finally turned the course into teaching how to write a little OS, and I call it TinyOS. So I'm going to take you, so in the first part we talked about how to handle catch exceptions, CPU modes, basically the way the CPU switches modes depending on an exception. An exception can be an interrupt from hardware or basically like a software interrupt dividing by zero and stuff. So we had an example, so I'll just proceed. So now once we got that, how do I go next? Oops, I screwed arrow keys. Or click on the little arrow. So the first part, yeah, we covered ARM registers, the modes, calling standards, exceptions, how to switch on an exception, basically what happens when an exception comes in, because the CPU shuffles things around, and that's key to understanding how to handle an exception, is where certain values end up after the exception. And then there's a vector table up in memory, which is basically a bunch of function pointers. And so the CPU saves some values, jumps through the vector table, and goes to your handler. And the handler you can handle data aborts, prefetch aborts, which are instruction errors, and interrupts. And then we started covering how to save context, but we didn't save the full context. So this part here now. In order to do task switching, we have to go over how to save the full context. And one of the other things we covered was basically adjusting the return address for the different exception modes, because the program counter tends to precede the instruction it's running on because of a pipeline. So the instruction it's being running on is the current instruction. However, the program counter is already ahead an instruction or two, trying to fetch the next instruction to get it into the pipeline. And then we ended with a data board example. So from there, oops. So what we need to do task switching is we need to set up we're going to define what a task is, and then we're going to set up a stack for each task. And then really all we have to do all we have to really do to switch to manage. So we use the stack to save we use the stack for the C function to run and to be able to do its calling, and its return, and it's basically every time you call a function, it's pushing values onto the stack. When you return, it's popping them off the stack. We'll also use that same stack to save the task's own context. And then when we switch away, we need to keep a reference to that context, and that's how we restore the function. So all we really need after we've saved the context is the pointer to the top of the stack where that context was saved. And so then we can save this by just simply saving the task's last stack pointer. We're good. That's all the information we really need to go then switch back to the task. And so we have I'll show you a little tiny scheduler that basically all it does is pick the next task pointer to use. And then we can restore the context, and now we're off. And then also too, this time we're going to introduce the timer, and the timer is going to provide the tick that's going to cause the interrupts, the task to switch. And so what I'm going to show you at the end is basically a little tiny multitasking OS that's going to flip back and forth between two tasks. So one of the things, some important points is each exception mode we go into also has its own stack, and that's kind of important for handling the exception mode. So each task has its own stack, plus the debug mode has a task, the interrupt mode has a stack, the exception handling. So every exception mode has its own stack, and so there's all these places we'll shuffle data around. And our main use is that it's going to be a little safe scratch pad for us to save values while we're handling the exception and switching between modes. It didn't work. So some simplifications for this little OS were no heap memory. And that's not uncommon in really small embedded operating systems, because a heap is actually pretty expensive data structure. It's a bunch of memory with pointers, and and you end up with problems with big gaps in your heap, and you start running out of memory. And so there's all these things. There's a lot of overhead in managing a heap. And so mostly what we're going to use is stacks and fixed allocated global for data. Also, by not using a heap, we don't have to bring in all that runtime code. The mode stacks are allocated up ahead of time. It's actually part of the build process. And another thing is task. Another simplification, and this is not actually a simplification. It's a given. Is tasks never return. So there is nowhere. Once a task starts, your initial task is either a loop, and we either block it or it continues to run. So we'll switch the task, and you'll see. All the task stacks are static globals, and we're just going every time the interrupt happens, we're going to switch tasks. So we're not going to do anything complicated. And so this is the overall pattern. So basically, so we start off with a reset, and the startup code we went over last time initializes different modes and jumps to main. So then main will allocate a stack for each task. We do some stack initialization because we're going to prime the pump for multitasking. We start the timer, and we call a function switch to first. So basically, everything that's in red is assembly code, and everything in blue is C code. So this switch to first task is a very small little function, and all it does is pop the first context, and that starts our task. And then the interrupt will come in, and the interrupt handler will be this task switching interrupt handler in assembly. And what it will do is save the current context, call the scheduler, and then pop the next context. And by the scheduler will basically switch the pointers to the stack pointers. And so then when it comes back to this function and it pops the context, it's now pointing to the next task. So you understand? So we just alternate between these two pointers and saving and popping context. And that's pretty much it. Once we get that pattern going, then the OS is running. One other thing to point out, we never return to main. So once we call this function, basically that's it. That code never returns. And in terms of hardware, this is just a little brief aside. So basically, the way hardware works on an ARM board is you can have multiple hardware inputs for interrupts. But you see there's timer 0, timer 1, UARTs are the serial ports, the power manager can interrupt, IC2 is like a little port that you might connect to boards. It's a very fast serial port. SPI is another real popular port, serial port, the real-time clock, bunch of other different things. There's a couple more timers, more UARTs. But anyway, up to 32 of these, and they're pass through a piece of hardware that ARM also designs and provides as part of the CPU core license is this vectored interrupt, and it produces either an IRQ interrupt or an FIQ. And FIQ is fast interrupt, and there's just a little quirks. It's basically a similar type of interrupt, and you don't have to worry about it right now. Just think of it as another type of interrupt. It just has more registers, but we primarily use the IRQ interrupt. And so when the interrupt comes in, the CPU then just simply asks the vector, the interrupt controller, which of these actually did the interrupt. And the reason it's called a vectored interrupt is that you just save a function pointer in each of these interrupt types has a little memory location where you can save a function pointer. So all you really need to do is retrieve that function pointer and jump to it. And then now you're jumping to the right piece of code to handle the type of interrupt that you got. And so it makes it really easy to handle interrupts. You just basically, you get an interrupt, you just query the controller, he gives you the function pointer, and you just jump to it, and that's it. So here's our task. It's pretty simple. It's a simple task. It's just an endless loop. And I put in a little delay here so that, because as part of it, like when you're using this, is that the CPU runs very fast, but we want to slow it down a little bit so that at human levels we can see what's going on. So we just put in a little delay that will slow it down a bit. And it just prints which task it is. So it's just printing, so one task counts up. So usually I have like one task that counts up and another task that counts down. And so then you can see on your screen, you know, it's which task is running by going back and forth. So then in main, we allocate, this is allocating our stack. It's pretty easy. So we allocate one block, so stack one, we pick a stack size. And then since C allocates from the lowest memory and up into high memory, but our stack is going to start at high memory and go down, we just need to calculate where that high memory location is. And so that's when, so the task one SP, so we're going to start at the top of that memory block, -1, because of, you know, and so then that gives us the top of the memory block that we've allocated. And so that's where our stack for the task is going to start. And then for keeping track of the different running tasks, we're going to have one global variable called current SP, and that's going to point, at the end of the interrupt, it's going to point to where that current task stack is. So as we go filling up, you know, the current SP is going to point to the bottom of that stack. And that's the thing we need to save when we save context, because we're going to save context, we're going to push it down, and it's going to point to the location where the context is saved. And then to save it, all we have to do is I just create a little array, and so the number of tasks, and all we have to do is save that pointer, and that's it. It's very easy. Later on, when we get into a little more sophisticated things and we start doing delays and semaphores, instead of just a simple array, we'll actually have a data structure, a little struct that has different other metadata about the tasks, and we'll also save it in an array. And but for now, the only thing we really care about is the stack pointer, so there's no point having a struct to complicate things. And so the general plan is we'll say, you know, when the interrupt occurs, we'll save the context to the stack. And we have to save the full context. So we have to do a little bit of shuffling around because of the way the register. There's one of the pieces of information that we didn't save last time was the saved program register. So the saved status register. And so to get to it, we need to shuffle some things around because you can't save from that register directly to the stack. You can only save from the regular registers to the stack. And I'll be clear when we do it. And then, yeah, so then the SPSR is basically right after the exception occurs, we're now in interrupt mode. In the interrupt mode's SPSR is the last status of the supervisor mode, which is where the task was running. So the tasks always run in supervisor mode. Interrupt hits, we flip into interrupt mode. And part of what this CPU does for us is save the programs. I mean the status register into the saved status register for us. And so we can. That's important because that's the last state that the task was in. So not only the values in the register, but what was its condition flags. And so then I'll show you how we juggle about to get to it to save that. And then also too, I'm going to go into more detail now about. So last time I showed you that there's on the ARM there are these there's two pair of instructions, load multiple and store multiple, that you can basically blast all the registers into memory. You know, so ARM. So if you recall, ARM is it's basically a register. Since it's a RISC processor, all the actions occur in the registers. You never do any actions directly against memory. You don't add against memory or anything like that. You have to pull it into registers. And so they also provide two instructions. So I can say that says save all the registers R0 through R12 plus R14 and R15 to the stack. And SP is actually R13. And so it will push all that to the stack, and then that's part of saving it. And so what's important is we need to see exactly what that does to memory, because that's where our context is going to be. and we just want to have a little more detail exactly what that instruction is doing. So this is how it does. So this is our stack. Let's say we have some dummy variables. You know, the function's already been doing some work, and that's where the stack pointer is. And so remember, the stack goes down in memory. So then we call this function store multiple the registers 0 through 12, 14, and 15, based off that SP, the stack register, and the pound sign means update that register when we're done. And so it will update the stack pointer. And so then you can see that after the call, the stack pointer is pointing down now where the registers are saved, and the registers are always saved in ascending order. So basically, the lowest numeric register is in the lowest memory location. And so this is what we get. And also, too, we didn't save R13 because that's not because he's our stack pointer, and that's what we're going to save elsewhere. And so that shows that. So right after we've done that, we've saved the majority of all the registers that we have, except the status register. And but anyway, so now you can see that if we were to pop, there's a dual instruction that if we load the the equivalent of this, the other pair, we would simply yank all that off the memory, put it into the registers, and reset the stack pointer. So here, this is what we're going for. This is the full context we want for each task when we save it. So we have the registers R15 through R0, but we also want to add the stack pointer. The status register. So the current condition codes that the task was involved in right at the moment of interrupt, we want to make sure that we save that, because it could be in the middle of some algebraic calculation or something like that, and the last it's because, for example, if it was doing arithmetic, it might be important that there's a negative. The last operation produced a negative value, and so you want to make sure that when you pop back to that context, it knows that there was a negative value that happened, and all that information is saved in this in the status register. So this is our goal: is when we do this, we want to do this. The complication is there's no instruction to directly go from the place where the status register is saved onto the stack. So we have to shuffle things around. So this is, so basically the same thing. This is, just iteration step by step where we're going to save the values and switching back and forth. This is sort of the plan. We're going to save some of the values to one stack. We're going to switch modes, retrieve those values, stuff them onto the correct stack, and by the first time we save, it's going to give us some space so we have some variables to work with. And the picture will show you more. So the first thing, so that's the IRQ stack. So when we first enter the interrupt, the IRQ stack is, our SP is pointing to the IRQ stack. We save, the first thing we do is we save R0 through R2 to the IRQ stack. And by doing that, now we've saved those values in those registers. That gives us 3 registers to play around with that we can now use them as variables. We don't have to worry about destroying data because we've saved the data. And the first thing, and so now what we're going to do is, now that we have 3 free registers, we're going to copy these other values. See, we're going to copy the R13 where it was before. We're going to save it, the original R13, which is the original stack pointer. We're going to save it up into R2. R14, which was the original return value, is now going to go to R1. And then finally, we're going to push the SPSR to R0. So that means we have 3 of those values, and all the other values are in the register. So now we're ready to switch modes. Oh, and before we switch modes, at this point, we're finished with the IRQ stack, so we can reset it. We can reset its pointer. But see, one of the things we did is that we pushed those guys, then saved it, so we know where R0 is right now. So this R13, right after we did this R13 points here. Then we save that R13 to R2. So now R2 points to this location. So now we know how to retrieve our data. And then we save all the rest. So now we're going to start shuffling things on. So we switched modes. So now this guy, the stack pointer now points to the task stack, but R2 points to the IRQ stack, so we can find our data later. So the first thing we do, so we switched, and then we use, we're going to use R2 as our stack pointer, and we're going to move these two values onto the stack. No, we're not. We're just going to move R1, which was the the return value of the stack. So it's the pointer where it points to the last instruction that was run in the task. So this is basically the task PC, where it was right at the moment of the return. And then this was saved for us by the exception, and this was the task return address. So if the task was running, it's usually been called by another function. It has both where it's at and when you were to return where it was going to go to. And so R15 is the pointer for the next instruction. R14 is where it was going to go to. And then now we can save the rest of these guys. And so now at this point we got 15, 14, 13 all the way down. Well, not 13. 13 we're going to use to save points to here right now. And then all these other values. And so one last shuffle is we grab those guys off the stack using R2, because R2 points to that guy. We save them into this register, which are safe now because we saved the data earlier. From here, we push them onto the stack. Now we got all those guys on there. And since we saved the status register in R0, that's our final step, is we push it to R0. So see, at this point, we've saved the entire context correctly. So it's a little bit of shuffling, but once you read the code and get it, it's not. And then the last thing we have is we set the current SP, which is a global, to where the stack is. And so current SP is going to point to this instruction now. And so that points, so it's pointing, this is the context of the task that was interrupted. So everything we needed to know to reset this task is right there in the stack. I mean, reset this task is in the stack. And at this point, we can call the scheduler. And the scheduler will save the current SP, pick a new SP, and then we can pop it. So this is the inverse. This is popping a stack. Given a current SP, all we have to do is set R13. So the scheduler will pick the next task. He sets the current global, the current SP, it's a global variable. The first thing we do is we push into R13. So now R13, our stack pointer, is pointing to the context. And so then we can pop the first thing that's on the stack at the bottom, because we're always going to start from the bottom and work our way up, is the stack context. So we push it back into the save, and then we pop the rest. And so at this point, if we return from this, the task is running. You see, because now we've restored everything identical to what it was there before. So that's this stack pointer will be automatically brought up to this point, which is where it was during the interrupt. The task will be ready to run the instruction that was here, ready to return there, because all the values are set correctly in the registers. So one of the things is, so I showed you saving the context and popping the context. Well, the question is, how do we start it? You know, the popping context function assumes that there was a context there. You know, it assumes that the stack was set correctly to be popped. And so what we're going to do is, when we originally set things up, we're just simply going to prime the stack with a fake context. That will help, and then all we have to do, we don't have to special case starting a task for the first time. All we do is just pop the context, and so that's the whole trick. It's just simply initialize, you know, a dummy context to begin with, and in it we set the function pointer that we want it to run in the right location, and we set this program status to the mode we want it to run in. In this case, it's the supervisor mode. And so when we pop that context, it will automatically start running the function we want, and it will be in the mode we want. And that just makes it easy, and it's actually, so I'll show you the function. It's not that complicated. Oh, actually, okay, so I'll do it step by step. So here's main. So there's mysterious init hardware, which you can talk to the hardware guys about actually how to set up the hardware, which is basically you go through all the ports and you tell them you're in this mode and you're that mode, and you turn on the timers and the clocks and all this other stuff. And it's a bunch of mumbo jumbo code that every time I work on this, people cut and paste for years. You know, because you start, the manufacturer figures it out the first time, and then they're saying, oh, this is the function you use to set up the timer, and so you cut and paste and put it in your code, and you're happy. Guys who are real hardware geeks get into it. I prefer, like, once the hardware's up and running. But mostly it's setting up the vector, setting up the timer, setting up the PLC, the PLL, which is the way the clock, the CPU actually has multiple clocks, and you get them all running. So then we have our current task ID. So as I didn't mention earlier, we have two tasks. So task ID can either be 0 or 1. We use task ID as an index into our tasks. And so basically, before we get there, we call this function initialize task. So we pass in the two stacks that we allocated above. I should have actually put it up here so you can see it. So we allocate the pointers to the array that we're going to use as stacks, and a pointer to the function that we want it to run. So I pass in a pointer to the memory location for the stack and a pointer to the function. I call my initialize task function. It returns a value that you save into the two arrays, and so then we can just pick which one of these functions we want to run first. And then we initialize the timer. So there's a little call. We basically set the timer up, and basically what we do is we tell the vector to interrupt. You know, not only do we want the timer to start every 100 milliseconds, which basically means 10 interrupts a second, and what function is going to be our handler. Then we pop the context. So at this point we call switch to current, which is going to pop the first context. And once we do that, the function, once we pop the context, we'll basically change all the registers to point to the first task. And so this function will never return. This code never gets here. This call is a single call. That's it. Never comes back. And if it did, it would just basically, a lot of times this is a fail-safe, you know? So the CPU wants to run something. So CPUs are never idle. So when you see the idle, you know, on your CPU, and say, oh, it's idle. No, it's not idle. It's simply running an idle function. That's a while loop doing nothing. And so what all it's showing you is the percentage of running that function versus your own functions. And that's what the CPU monitor is doing. The CPU on itself is always running. In the embedded world, they're finally starting to do things like, oh, we'll slow the CPU down so it runs really slowly and doesn't drain all the energy. And some of the more modern CPUs, actually, you can freeze the clock and have some interrupt, wake it up later in the future. But for your desktop, always runs. And so a lot of times when you're developing, especially you put these little wild ones so that it doesn't go off into oblivion and you get confused as what happened when you made an error. It will just simply stop here, and then you know, oh, gee, if I'm here, I must have made a mistake somewhere else or something like that. Because that's one of the things that makes embedded programming hard is there's no debugger. I mean, well, there is a debugger, but you can get into a state where you don't know what happened. And so you want to have like little fail-safes and blocks and happy places for the code to get stuck in. And then you can say, oh, I see, you know, and you don't completely destroy all your values in your register. And then so here's how we prime the stack. Here's that calculation. This finds us, so given a block of memory where we've allocated down here, we calculate all the way, figure out what the top of it is, and that's what this calculation is. So it shows us the top of that memory location. And then we're gonna cast it as a pointer. So now we have a pointer to the top of the location. And now we're gonna start filling in dummy addresses. So this is the function pointer that came in, and it will go into the R15 spot. And then everything else, you notice I just kind of numerically put the values. And this is just mostly for debugging. You know, like if I'm curious to see, did I initialize the stack correctly, I should see these values in the array. You know, I mean, in the registers. I mean, they can all be 0, you know, but a lot of times it's useful, you know, to verify, to leave little cookies in memory when you're debugging, because that way you can freeze the debugger and go look somewhere and see, well, did it actually do what I wanted it to do? And so that's very helpful. A lot of debuggers will do this, will actually leave little bits around, you know, so that they can verify that certain things have been touched and actually run. And then finally, this is a macro that simply has the bit pattern for the initial mode we want it to be in, and it's going to be this is the value that's going to be pushed into the status register. So this is our dummy task. I mean, our initially primed stack is basically, once we get down to here, we've primed the stack and it's ready to be popped. We return that value, we store it, we're good. So this is that task. So we have one function. This is starting the first task, and all it's going to do, it takes the current. So this is the current SP, which was a global. We put it into R0. We push its pointer into SP, and at this point we do this load multiple of everything off of using this guy as our. The first value on the stack is the status register. So we need to pop it by itself and stuff it. This is the special instruction. So we're stuffing that value we saved, the mode that we want it to be in, and we push it into the save status register. And this is a special instruction for moving things in and out of status registers. And with this instruction, here, this is the magic instruction that gets everything running. We say basically pop all these registers, and we notice you see the PC, so that will cause the PC to be pointing to the function we want it to run. Update the stack pointer, and this special little symbol here means, and also copy what we put in the saved register into the actual status register, and that makes it all run. At this point, this is, as soon as it runs this, we've left this function and we're running a task. The C code is up and running, all the registers are set correctly, we're at the right memory location, and the context and the status register is set correctly. And so we're in the right mode. So this is used to switch modes, and there's a lot of stuff in assembly code where you have little special magic symbols that you just have to know. And so basically we've set the timer. Actually, this slide should have probably gone up ahead to every 100 milliseconds. So basically 10. So if you're watching this on the screen, it will switch back and forth 10 times a second. So you'll see one task run, another task run, another task run, basically 10 times a second. And so basically the timer will cause an interrupt. The interrupt will jump through the IRQ vector, which we set up and went over how to set that up on the first deck. But anyway, there's a special memory location the CPU always jumps to because of whatever mode it is. So at IRQ, it always reads the exact same memory location. So all we have to do is save a function pointer there. It calls that function pointer. So then it calls it, and what it ends up calling is our context switching assembly function, which we've called switching IRQ handler. It's, creative name. And then the handler will save the context, call the scheduler, then restore whatever context the scheduler picked. And so all the scheduler has to do is set the current SP value to whatever task it wants run. And so this is the context switch handler code. So this is all of it. So we have to adjust the return value, and then once that's this is the part where we save some of the values off to one side. We save the status register off to one side, and then we save the stack pointer to R2. And we reset the IRQ stack, because at this point we're in IRQ mode. We reset its pointer. This call causes us to switch into supervisor mode. Now we start reversing things, and we start basically pushing everything onto the task stack, and all the way. So this is basically the shuffling part, and we pushed everything onto the context. By this point, the context has been saved completely. So this is the instruction. So basically we prime a little bit onto one register on one stack, we push it over, shuffle it, and by the time we get to here, everything's been saved correctly onto the stack. Now this is the function call. So basically we're going to put this, this says put the stack pointer into R0 and then calls the scheduler. So the scheduler is going to be called, and its first parameter is going to be the stack pointer where the context is saved. And so this will call the C function. The C function will go off and pick which scheduler, and it's going to set this global. When we come back, we take the value from the global, we simply set R0, we set our stack pointer with it, and now we can, we pop the first, and this is the same as the switch context. We pop the first value, which is the save status register, into the right save status register function, and we pop everything else, and we've switched tasks. Yep?
Do we have to worry about what happens if an interrupt request comes in the middle of the context switch?
Technically, no. That's a good point. A good question. Whenever an exception happens in the CPU, it turns off all interrupts. Okay. There is a thing where typically it will turn off all interrupts but FIQ, and there is a sort of no. I think no. It turns off all interrupts. Yeah, it turns off all interrupts. Okay. And you can set it up so it doesn't. The FIQ interrupt can interrupt the other one, depending on the mode. Typically what you do, if you want to do, it's called nested interrupts. You deliberately have to save the context, turn on the interrupts, and then allow yourself to be interrupted during the interrupt handler. But typically, the interrupt comes in, you turn off all interrupts are turned off for you, so you don't have to worry.
Okay.
Yeah, because otherwise it gets too complicated. You'll destroy your own data.
Does it queue up interrupts it would have sent while they're turned off?
Yeah, that's what the vectored interrupt handler does. So typically you won't miss an interrupt. You know, and so because of that, you want this code to be quick. You know, typically you want to go pop in, pop out, so that, and that's the latency on an embedded processor. How many instructions is it going to take? Once you get an interrupt, how long is it going to be before you're ready to take the next interrupt? And so when you start talking about, you know, real-time operating systems, you try to make basically that period of time to be bounded. You know, like so Windows is not a real-time operating system, because once it takes an interrupt, it might go off and decide, oh, I'm going to mess with the paging system and do this and that and come back. And so you're going to get longer delays. With embedded operating system, this function is critical. You just try to make it as short as possible and do its job and always come back as quickly. But it's not very long. And then the scheduler is really easy. So the scheduler, this is a requirement for the hardware. We basically just write this value into this register, and that tells the timer to be reset. So we're not going to get another interrupt for another 10 milliseconds. So there is wiggle room here. 10 milliseconds is a long time on a CPU. You know, we save the current stack value into our tasks, and then I'm going to use I have this current task value. I'm going to increment it, and as long as it's not more than, I'll reset it. So it just loops around. So basically, this is sufficient to do an itty-bitty round-robin scheduler. You know, it runs each task one and after the other, and just keeps looping around. So you can have 10 different tasks all set up exactly the same, and it will just keep looping around through them. And each task will get 10 milliseconds. And then the requirement is that it picks a task and sets current SP. And this is what the other function is going to use to figure out, it's going to pop this context that was saved here. And at that point, this is a preemptive multitasking system. I mean, it's not very sophisticated and only runs a couple of tasks, but it is preemptive, because the interrupts will come in and we can handle the interrupt. The interrupt in this case, we only have one interrupt, which is the timer. But when the timer comes in, we switch codes and we go back and forth between the two tasks and stuff. So this is the basic, the minimal context switching that we can have. So summary, tasks don't return. Each task has its own stack. Stacks are allocated globally, statically and globally, so it makes it easy to see it from the assembly code and the C code. We prime the stack with an initial context. we turn on the timers, the timer causes the interrupts cause a call to our context switching function, it saves the context, calls the scheduler, and then returns whatever context was selected by the scheduler. And then the scheduler's responsibility is to save the pointer to the context from the last context into its little array and simply pick the next context to be popped. And then the switching function then simply restores the next context. So here, before we go to next steps, any questions? Maybe I should slow down. Huh? Yeah.
What additional stuff do you have to worry about when you have multiple cores on a CPU?
That's a good question, and I've never worked at this level on a multi-core, but I worked, when I was a kernel PM, we were just starting to do multiple cores on Windows CE, and part of it is you have to be, each core will have its own, you probably have to set up multiple stacks and then have different functions. No, you have to, I think there's more hardware support that lets you know which core interrupted, where it interrupted. You have to make decisions as to which core is going to run your code, your kernel code. So there's two different modes. One is like symmetrical, where your kernel code can run on either core, or you have asymmetrical, where you say the kernel code only runs on core 0. And there's different pros and cons and stuff like that. But it is a considerably more complicated problem. And there's also considerably more hardware support for that scenario. You know, ARM7 has, basically has minimal hardware support for just covering what we just did right now. Any other questions? And so what I was going to show you, if you guys are interested next time, if you want me to continue, is the idea of quantums. So right now we're switching tasks exactly on the interrupt beat, right? Well, that's not very practical. That means we can't have a clock that runs faster than the amount of context switches we want. So what you can do is you save some metadata for each task. You have we use a little structure that has some metadata, and it just simply has a counter. Every time a task gets interrupted, we count how many times it's been interrupted. And we use that count. We say we'll come up with a policy that says every 10 interrupts we switch context. And so that policy of saying, oh, every 10 interrupts, that's how long it's going to run, is called a quantum. So if we can say so basically we can have the timer run at once every millisecond, which is useful for doing like timer counts and stuff like that. Because if we know the interrupt's coming every millisecond, then we can simply have a little clock running off to the side, and we know that it's being updated. Every 1,000 updates is 1 second, and all our calculations work out. But we may not want to switch tasks every time. So we simply count and say, oh, when we get up, we're going to wait for 100 interrupts before we switch. And so we just have for each task, we'll have a little counter that says how many times he's been interrupted. When we get to the magic number that we've decided on, let's say 100, then we actually complete the context switch. So the scheduler would check. Before the scheduler switches to another task, it would check what the current quantum count is.
So if I have my timer running at, say, the original once every 10 milliseconds to switch back and forth, and I have one of my tasks that wasn't doing much, and so therefore it's kind of wasting its 10 millisecond time window. Is there a way to be more efficient there? Because this is basically says, okay, swap now. Do you just adjust it down and say all tasks run at 1 millisecond? Or is there a smarter way to do it?
There is a smarter way, and that's exactly what these two other things are. To do it, no, it's a great question,
right?
Yeah, perfect. So quantums gives us this window, So now we have, a clock and the interrupts are separate, and we can have a policy and stuff like that. The other thing is, what if we have a task and we know, God, we don't have to do anything for another, 5 seconds. Well, we add another piece of metadata called a delay count, and we have a function called, set the delay count on this task. And so then the scheduler gets a little more complicated. Now we introduce the idea we have a list of things that are running and a list of things that are waiting. And so when a function calls the delay, we take it out of the running list and we put it in the waiting list, and every interrupt we decrement its weight. And when its wait gets to 0, then we go back. You know? And so that's delays. And there's actually another little thing even before delays, which is called critical sections. One of the things we want to do to implement these guys, we need to be able to shut off interrupts while we're moving data around. Because if we get interrupted in certain parts of the kernel when we're doing things like moving it from one list to another, it could cause corruption. And so we introduced two little functions that give us a thing called a critical section, which is we call the first one, it turns off interrupts. We can move our data structures around. And then we call the second one called exit critical section, which will turn interrupts back on. And that's a thing that should be on this list. But what we implement that, they're actually very simple functions. And then the delay, if we turn off interrupts, then we can move it from the run list to the wait list, and we don't have to worry about being interrupted while we're doing some of the work. So a lot of times in a real-time kernel, what you do is you go through all your code and you say, I can be interrupted here, and it's going to be okay, you know? But if I get interrupted here, this is going to be bad. And so I turn off interrupts just around that little block. And so those are called critical sections. And typically, you try in the overall system to minimize it to the kernel, you know? Or in a couple of places in your own code where you're going to do something very quick. Because the idea is to try to keep interrupts on as long as possible. But definitely when you're moving around globals and you're doing shuffling things, there are a couple places where you can't handle being switched away from context, you know? So you make sure you turn off the interrupts during that section. Anyway, so with delays, we now have a wait list for things that are being delayed and a run list. And so basically every interrupt will decrease the delay count, but the scheduler won't run it. It won't actually pick a function waiting on the wait list. When it gets to when it gets to 0, it will move it from the delay list and put it back on the run list, and then then it will be part of the round robin circle. The next level is introducing semaphores, and in semaphores you can now have and this is like the one part of this that is computer science. Dijkstra in 1965 said that semaphores are essential for operating systems. So they're the essential data structure to actually have true multitasking. And what you can do with a semaphore is now, for example, if you run the code that we showed you right now, each code prints to the serial port. But what will happen is that you will see like one guy's halfway through writing his sentence, and then the next guy's running. You know, blah, 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 blah. And then he's interrupted, and you see the previous sentence get interrupted. So they're basically interrupting each other's output streams, you know? Because interrupts are coming in, whatever. But what we can do is we can protect the output with a semaphore. And so then they compete. So each task has to grab the semaphore, and then as long as he's holding the semaphore, nobody else can interrupt him, and he can complete his printing, you know? And if another task comes along, and actually he can be interrupted, but the semaphore protects this block. And so if another task wants to print, he has to grab the semaphore, but if somebody else, it's like a baton, and you're just passing it back and forth. The guy who has the baton can finish whatever he wants to do until he releases the baton. Then the other task comes along and grabs the baton. So if a task comes along and the baton's not available, it's called blocked. He gets put on a block list and has to wait until the baton is released. And so that way you can protect, and by simply introducing those a semaphore around the print function, then each sentence will be its own complete sentence. It's very obvious when you run the example, you know. So without the semaphores, the output is interleaved in the middle of a sentence. With the semaphore, each sentence is complete, you know. And so with these things, basically, once we've completed, you know, the quantums, the critical sections, delays, and events, we actually have a really useful little operating system. So if you guys were interested, I could do another day.
Yes, I am.
Okay.
I have a question.
Sure.
It's a very simple question. Where do you buy the elements?
Oh, you can go to olamx.com or go to Sparkfun.
Sparkfun?
Yeah, Sparkfun. There's a couple of places. Adafruit, Sparkfun, Olamx directly.
Yeah, I was checking Olemex, and they're sent from overseas.
Yeah, it's from Bulgaria, so that's why you can buy from some of the local guys like
That's
Sparkfun.
what I was asking.
Yeah.
While you were talking about, I was looking at here. This 135.95 euros. Okay, great. I'm buying from overseas. Great.
Oh.
So, is there any local that I can order? Then, of course, my first choice was Amazon, and of course, Amazon.
No, yeah. So I would look on Sparkfun. They have a lot of boards, and basically everything I've talked about will work. This is all ARM7, but there's tons of ARM7 boards, and the concepts are very similar across all CPUs. The only difference is if you switch CPU families, you'd have to figure out what they call their register and what their conventions are. But the concepts are almost all identical. And so one of the things about an ARM7, I like ARM7 in terms of teaching because it doesn't support virtual memory, so it doesn't have a memory manager, and that makes it a lot easier to work with. You know, it's basically one big flat memory space, and so the register sets and the instruction sets are pretty simple. You know, and I like ARM register. I like ARM assembly a lot, and probably because it's very similar to the 6502 that I learned years ago. But yeah, it's all just load and store, and it has a couple of special little instructions for certain scenarios. But otherwise than that, it's a pretty good learning process, and it's probably one of the most widely shipped CPUs in the world. And in fact, our smartphones, many smartphones actually have two CPUs. One for the UI, a sophisticated virtual memory CPU and all that for the OS, and a little tiny one just for the radio stack. It keeps the cell phone working.
Question. Does the kernel know when you ask for a semaphore that somebody else has it, and would it just interrupt you right then and there?
No, so that's the thing. The kernel is actually the one who manages the semaphore. And so basically, you provide two kernel functions called acquire. Either some people call it pend and post, acquire, release, and so you basically make a query. You say, I want the semaphore, and at that point, this is where the critical sections come in. At that point, the kernel turns off interrupts, and then he checks who has is the semaphore available or is it not available, and if it's not available, I'm going to take you from the running list and I'm going to put you on a block list, and then I'm just going to return back to whoever else is runnable,
So if somebody doesn't release the semaphore, the system locks up?
Well, it would only lock up for the functions that have tried to request the semaphore. So you could have 6 functions, and 2 of them are competing for a semaphore, and one of them doesn't release it. Well, that only means the other guy's blocked. Only one guy's blocked. But you can get into these weird. If you're not careful with how you use semaphores, you can get into a deadlock where A wants semaphore that somebody else is owning, who's waiting for this guy, and then all 3 get blocked, and none of them can run. It's sort of like and so that's where it starts getting. And then you can get into run condition, race conditions. Basically, every function is racing to get that semaphore. And but the moment someone gets the semaphore, the OS has another list. It says these are the blocked functions. They don't get to run until they're released. And so on the converse, the function that releases the semaphore basically says, okay, I got called, semaphore's back. Is anybody waiting for the semaphore? And so usually you have a list per semaphore. You say, oh, this guy's waiting for the semaphore. Hand it to him. He's now runnable, and he gets moved to the run list, and then he gets scheduled to run. And then this is pretty much the basics of a fully functional OS. And there's a website, tinyos.rockfishnorthwest.com, where I have the source code. Yeah, no. TinyOS, I couldn't get Rockfish. It's a chain of restaurants in Southwest.
So what core or what processor is the Raspberry Pi use?
It's probably an ARM9.
Okay.
Yeah. Or no, actually the Raspberry Pi. I think they've gotten pretty sophisticated. I think it might even be a Cortex, which is a pretty beefy little CPU.
Okay.
Yeah.
What is Raspberry Pi in this context?
Oh, it's a $30 Unix board. So basically, it's a Cortex CPU with like an Ethernet and like 2 ports exposed to that. Yeah. Yeah, they're pretty self-contained little things. What's nice about the Olimex board that we used in class is that it's based around a processor that's really designed for embedded, and so it has all these ports that are exposed. You know, there's all these GPUs and things like that, and as long as you follow some basic electric rules, man, you can tie all kinds of things to it and drive all kinds of things with it. You know?
Are there any cheap boards like the ARM7 that are in that price range? I mean, because he was mentioning, they're a couple $100, whatever. But I mean, the one nice appeal about the Raspberry Pi, right?
Well, there's a new one called the BeagleBone, and it fits well. So that some of the cheapest is the Arduinos, but Arduinos you don't program at this level. They have their own like little tiny mini kernel that's already in firmware, and so that's why they become really popular because they're the barrier to programming is pretty low. But then there's a BeagleBone which has the same pinouts and configuration that's compatible with a lot of the Arduinos, and it runs an ARM7 or ARM9 or something like that, and you can get it for $70. So there's like a Beagle board I know that was out, and it was pretty beefy for for just under $100. I mean, you can do 3D graphic videos and stuff like that. Yeah, yeah. But you know, so the main thing is that we used an ARM7 because it's easy to set up, and because one of the things that makes this hard, especially for class, is the tools are fussy and getting all the tools up and working and stuff like that. Okay. Cool.
Thank you.
Oh, you're welcome.